Okay, where was I? Talking about the D block elements. The idea of valence electrons is a little tricky. The electrons that they have in their outermost energy level are the S block electrons. So for the fourth period D block, then it would be their 2 4s electrons, unless they're one of the exceptions in which they have 1 4s electron. And so things just get complicated there. So we typically talk about our valence electrons. When we're talking about a particular element's valence electrons, we usually limit it to the S block and the P block. And we kind of skip the D block. So group 1 has 1 valence electron, group 2 has 2, group 13 has 3, 14 has 4, etc. Why do we not have enough? Am I missing something? Yeah, we're somehow missing. Okay. That's weird. Okay, this picture is weird. We're just going to put 3, 4, 5, 6, 7, 8. Okay, with group 18 having the full octet, the full S and P shells, which is a particularly stable configuration. So, for example, this might be the kind of question that you might see on a paper 1. It says an atom of bismuth. Bismuth is atomic number 83. You don't have to know that Z is atomic number, but it's probably a good thing to try to get in your head. How would we figure out the principal energy level number for bismuth? What would we look for on the table? Yeah. Yeah, so this is going to be the period, or the row. And how are we going to figure out the number of valence electrons? Yeah, it's going to be the group, but minus the D block. Right? Okay. So for bismuth, what period is it in? 6. And how many valence electrons is it going to have? 5, because again, we're it's in group 15, but we're subtracting out those 10 D block elements. And so we're going to end up with choice C. So that's a pretty simple kind of question, but you are likely to see something like that on the test. Okay, we were just talking, we talked previously, and we were just talking in the warm-up about metals, nonmetals, metalloids. And the fact that the majority of the elements in the periodic table are metals. You might get a question like this. It says, which element is a metalloid? And you might say, hi, what do you need? Small ones, yes. Okay. So you might be looking at this question and saying, but I didn't think we had to memorize what the metalloids were. And you don't, because it's going to be obvious. If you look at where cobalt is, cobalt is in the D block, so it's very clearly a metal. Cesium is the one that was in the warm-up. That's in our, is this what kind of size you're looking for? Okay, great. You're welcome. Cesium is in the S block. So definitely a metal, because everything except for hydrogen in the S block is a metal. Einsteinium is down in the F block, and so that is also going to be a metal. So you don't have to memorize that arsenic is a metalloid. You just have to know that none of the others could possibly be metalloids, and that arsenic is in fact going to be the answer to that. So you won't have to memorize the staircase, but you just kind of have to know where the about where the metalloids are, and they won't give you a question of like arsenic versus tin or something like that. It'll be obvious that it's not a metalloid, or that it is a metalloid, or that it's not a nonmetal, something like that. Okay, so there are a few terms, names of groups in the periodic table, and again, this is listed on page 2. That you should be familiar with. Some of them we're going to go into in a great deal more detail going forward in this topic, but also there just tend to be terms that are used pretty frequently. So Our group 1 minus hydrogen is called the alkali metals. These are our most reactive metals. And we'll be talking about trends in reactivity and some other things within that group of metals. Alkaline earth metals are our group 2, and they are similar to group 1, but a little bit less reactive because they have that full S subshell. So they're a little bit less willing to give up an electron than the group 1 elements. Our group 17, the halogens, those are the most reactive nonmetals. They are so close to having that full octet. They just need one more electron, and they are going to get it by any means necessary. Our noble gases, group 18, we've already talked about those in terms of our electron configurations, so you should know that term as well. And then the D block is also known as the transition metals. You don't have to know that zinc is actually not a transition metal. That's a HL material, but so generally speaking, when we're talking about transition metals, we're talking about the D block. And then there's also the lanthanides and actinides. So our actinide, these are our F block rows. Our actinides are the last row in the F block that would be in period 7 if we made our wide periodic table. And those are going to be, many of our radioactive elements are going to fall in that row, including uranium. The lanthanides, the row above it in the F block, are also sometimes called the rare earth metals. It includes things like neodymium, which is what we make these fancy, very strong magnets out of, which we'll be talking about in a second. They're not necessarily all rare, actually, but that was the name that was given to them. These terms are less important than knowing, say, the halogens, the alkali metals, the transition metals. Those you should know. We've already talked about this, the electron configurations. So just remembering that helium is also in the S block, even though it sits at the end of the P block. That's the only thing I would just reinforce with that. And also hydrogen is sometimes in some periodic tables just taken out of group 1. It's in group 1 because it has one valence electron, like all the other group 1 elements, but it otherwise has very little relationship to the properties of the other group 1 elements. So sometimes you'll see hydrogen just kind of like by itself in the middle somewhere. Yeah. Yeah, no, because it really doesn't have the properties of 17 either. It does like very, very occasionally form a -1 ion when it is put together with one of the alkali metals. But it doesn't really act like either of those groups. So yeah, it has some similarities, but yeah, it's kind of its own little entity. Helium is more like the other noble gases than hydrogen is like any other group. Okay, we've actually done this, looking at electron configurations and then finding where it is on the periodic table. Here's another question that you might get, another paper 1 type question that you might get. It says, which statements about atomic structure in the periodic table are correct? Statement 1, an element in group 2 has 2 electrons in its valence energy level. Is that a true statement? Thumbs up, thumbs down. Yeah, okay. Element in period 3 has electrons in 3 energy levels. Thumbs up, thumbs down. Seeing mostly thumbs up, that is correct. And the element in group 2 and period 3 has an atomic number of 12. Thumbs up, thumbs down. Look at your periodic table. Yes, it's magnesium. All right, so this, I strongly recommend that you, when you have questions like this, that you just go through each statement at a time and only then look down at the answer choices. There's really no point in looking at the answer choices until you've evaluated the statements. There may be situations where you know 2 out of 3 of the statements and you're not sure about the last one, and the answer choices given might help you narrow it down, but this is really the only way to answer these questions. Okay, so we get trends. in these different properties, both going across a period and going down a group. And we're going to be talking about trends in a lot of different types of properties, some ones that we talked about in honors chemistry and some that we did not. But you really should know the definition of periodicity, okay? When we talk about the periodic table, or we talk about periodicity as our topic title, it has to do with repeating patterns. And particularly for the periodic table, we're talking repeating patterns in the properties of the elements. And that's true for any other type of word based on the same root. So we are currently in fifth period, which happens every day at this time, except for Wednesdays. So we call them periods because they happen periodically. You often call menstruation getting your period because it happens periodically every so many days. And so it's the same idea with periodicity. We're talking about periodic repeating patterns. And these patterns underlie a lot of what makes elements react in different ways, what makes them bond in different ways. And so it's pretty important, which is why we have a whole topic about it. We already did that. Okay, one of the things that's important to understand, and you guys did a whole packet about this in honors chemistry, but for some of you that was a while ago. So I just want to review these basic ideas about Coulombic attraction, because this is really the force that underlies most of the trends that we're going to be talking about. So understanding this will help you deduce what the trends are rather than having to memorize them. So being able to figure something out is always better than having to memorize it. That's not to say that memorization doesn't work. So Coulombic attraction, Coulombic forces are the forces of attraction and repulsion between charged particles. Okay? Things with the same charge repel each other. So two electrons are going to not want to be near each other. Two protons generally don't want to be near each other. There's a whole nuclear physics underlying why the protons all get stuck in the nucleus. But mostly we're going to be talking about electrons here because, well, it's going to be both. It's going to be talking about the force of attraction between the protons in the nucleus and the electrons around the outside. So you can feel that force of attraction. You can see it by looking at static electricity. I often use magnets as a metaphor for this. It's magnetism and charge are not exactly the same thing. They don't work exactly the same way, but there's enough similarities and you're all used to using magnets, so it's a little bit easier to tell. So if I have two magnets and I put them on the sides that are attracted to each other, if I hold them far away from each other, there is a force of attraction, but it's so small that I can't feel it. Okay, I don't feel these two magnets coming together, and the force due to gravity is stronger than the force of attraction, so if I drop them right now, like they're just going to drop separately onto the floor. As I bring them closer together, I start being able to feel in my fingers, then in this amount of strength that it takes me to hold them separately, I start being able to feel that force of attraction. The closer they are, the stronger it is, the harder it is for me to yank them apart, okay? So the attractive force increases as we get closer together and decreases as we get further apart. That's just a physical law, okay? Coulomb's law. The other thing that's going to affect that force, one of the other things that's going to affect that force, is how big the charge is. Okay, so if I have the same charge, then it's the difference in forces is going to be different due to distance. But if I have different charges, that is potentially going to trump the effect of the distance. So if I have two magnets on each side and I'm trying to keep them from sticking together when they're really close, it's harder than if I just have one on each side. Okay, and you can feel that physically, and you can sort of see that in your head. So those are the things that those are two of the things that are really going to affect those interactions between the protons and the electrons, and that's going to affect things like the size of the atom, because the size of the atom is dictated by how far away the electrons are from the nucleus, right? Just like the size of your pizza depends on how far the crust is from the center. So we're really looking at what's going on with those outer valence electrons related to the forces of attraction between those electrons and the protons in the nucleus. Okay, so it's important that you remember that distance has an inverse relationship, charge has a direct relationship. So as we increase our distance, the force is going to go down. Okay. As we increase the charge, the force is going to go up. So recognizing that, taking that into account every time you're thinking about how a particular property is going to be affected by going across the table or going down, going across a period or going down a group, that should be in the back of your mind. Okay. There's another thing that we didn't really talk about in honors chemistry. And that is this thing, this is page 6 in your study guide, that's this thing called electron shielding. So these Coulombic forces are not just affected by charge and distance. They are affected also by how many electrons are between your valence electrons and the nucleus. So if we have electrons just in the first energy level, there is nothing between them and the nucleus. So the effect of the positive charges in the nucleus is whole, essentially, on those electrons because there's nothing standing between them. Okay? Once we get into the second energy level, not only are we further away, which weakens the force of attraction, but we also have these negative charges in between. And that shields that force of attraction from the protons a little bit. The further out we go, the more electrons we have in between the outer electrons and the nucleus, the bigger that shielding effect is going to be. Okay? And there's actually a lot of complicated bits to this if you get into higher level, not even HL, but like college chemistry and beyond and atomic physics. There's actually a lot of subtleties to where those electrons are, the sublevels. There's effects of shielding on electrons in the same energy level. But for our purposes, we're going to boil this down to the energy levels underneath our valence shell are the ones that are going to be affecting the shield, that are going to be shielding our outer electrons. Okay. So as we go across a period, the shielding is going to be the same because we're just adding valence electrons to the outermost shell. We're keeping the same number of electrons in our core energy levels. And so we're going to have that same amount of shielding. As we go down a group, the shielding is going to increase because we're adding more energy levels. Okay? Let's see. This is just another picture of this idea of shielding, and it comes from the fact that there's this force of attraction from the nucleus, but there's also this force of repulsion from the electrons in between the valence electrons and the nucleus. And that's really where the shielding comes from, is that balancing out of some of that positive attraction with some negative repulsion. Okay. Okay, so what we end up with is these concepts of nuclear charge, which is really just the number of protons. That's just Z, okay? That's the nuclear charge, the atomic number. And effective nuclear charge, which is how much force are the protons in the nucleus really exerting on those valence electrons. And that's going to be dependent on what energy level those valence electrons are in. And that's partly because of the shielding of the core electrons. So it's distance, but it's also the fact that you've got all these negative charges in between you and the protons that you're attracted to. Okay. There is in this in your study guide and in the slides that Mike Jones has for this section, he talks about a way of calculating the effective nuclear charge. That is not something that you need to be able to do on the exam. What you need to be able to understand is that the effective nuclear charge goes down as there are more shielding electrons added. So you just need to understand the effect of those core electrons on the effective nuclear charge, that it decreases the effective nuclear charge. Okay? But you could come up with a pretty simplistic calculation by saying we're just going to take the atomic number minus the number of shielding electrons that are in the lower energy levels. And that would give us essentially an effective nuclear charge. Where do I have the, yeah, so in that sort of simplistic idea, the effective nuclear charge is going to increase as we go across, even though the shielding is staying the same. So the shielding is staying the same as we go across a period, because we're staying in the same, we're adding electrons to the same energy level. Our valence electrons are in the same energy level. The effective nuclear charge is going to increase because we're adding protons with each spot that we move along the game board or the periodic table going from left to right. As we go down, though, the shielding increases and the effective nuclear charge is pretty similar. Okay, so if we look, for example, at beryllium, magnesium, and calcium, these are all group 2 elements. They have 2 valence electrons, and beryllium has 2 electrons in the core, okay? So there's a total of 4 electrons and 4 protons. So you would say that the nuclear charge is 4. But if we subtract out the shielding electrons, we would say the effective nuclear charge is plus 2. Okay? If we look at magnesium, we have 12 total electrons and 12 total protons. Okay? If we subtract out the shielding electrons, then our effective nuclear charge is again plus 2. And same thing with calcium. So as we go down a group, our shielding is increasing. Our number of protons is increasing, but so is our shielding. So our effective nuclear charge is remaining about the same. That's as far as you need to understand the effective nuclear charge stuff. There's actually this equation is way, way simplified. There's a whole set of different types of calculations of effective nuclear charge, some based on where the electrons are in the sublevels, and then also there's a whole set of like quantum calculations that are probably more accurate, that none of which you need to know about. Okay. Okay, so if we are looking at, this is another question that you might get, another paper 1 style question. Which of the following would have the same numerical value for all elements in the same period? So everyone is in the same period. What is going to be the same for all of those? So answer choice A says highest energy levels occupied. Choice B says energy sublevels occupied. C says orbitals occupied. And D says valence electrons. So which of these is going to be true for elements in the same period? Raise your hand if you think it's A. That in the same period, we're going to have the same number of highest energy levels occupied. Okay. What about B, energy sublevels occupied? Anyone think it's B? How about C, orbitals occupied? How about D, valence electrons? Most people are not interested in taking a stand on any of these. Okay. They're in the same period. What is a period? It's main energy level. The row on the periodic table is the period. And that corresponds to the main principal energy levels. So the answer choice, the correct answer here is going to be A. Okay, if you picked D, then you need to refresh your memory about what a group is and what a period is. All right, get that in your head. Groups are the columns, periods are the rows. Okay. All right, I think, yeah. So the next thing we're going to get into tomorrow is starting to talk about, okay, we've got this idea of effective nuclear charge, we've got these ideas of groups and periods, and this recurring pattern that keeps coming back over and over again that makes the periodic table periodic. So when we come back tomorrow, we'll start talking about what some of those properties are that change periodically. And we'll start with the ones that you already know from honors chemistry, and then we'll go from there. Any questions right now? Okay.